Back. In my previous video, I have seen what is the analytic function. In my previous video, I have seen if a function be analytic, that means if z is differentiable in the open ball PAR where r greater than 0, that means if fz is analytic, that means there exists a locally power series. Also, I had seen the relation between power series and analytic function. Let fz equal to the power series ANZN be the power series with radius of convergence r. Then, if f is differentiable on this ball B0r, furthermore, f prime z would be differentiable in this ball. That means the power series can be differentiable term by term in the disks of convergence. So, a function be analytic means power series be differentiate term by term in the disks of convergence. And today's goal of this lecture, today I will see what is actually differentiation. A function which defined from R to C, f is differentiable at the point A means, we all of us know, limit h tends to 0, f of a plus h minus f of a over h exists. And if this limit exists, and if we denote this limit as a alpha, then this alpha always would be unique. And this is called derivative of f at the point A, and it is denoted as f prime A. We all of us know this is. But today's goal of this lecture, today I will see what is the differentiation in real line. Now I will see what is the differentiation in real line. This is actually today's goal of this lecture. Today I will see what is the differentiation, because whole complex analysis depends on differentiation. If you know the differentiation in briefly, then you will understand the complex analysis in better way. At first, I will say what is the differentiation in real life. In my previous video of multivariable calculus, I have defined differentiation in real line. At first, I will highly recommend you, if you don't see my previous video, first see the previous video. Then today's video would be so easy. Just see the playlist of multivariable calculus, then you will see differentiation in real line. Just as a review, we all of us know if f is differentiable at the point A, that means limit x goes to A, fx minus f of A over x minus A exists. We all of us know if f is differentiable, then this limit always exists. Third, fx minus f of A over x minus A, consider this is as gx. And f is differentiable means, in my previous video I have seen limit x goes to A, this gx, since this limit exists, means consider this value of the limit is lambda. That means that imply absolute value of gx minus lambda less than epsilon. This is the definition of limit. And here gx means fx minus f of A over x minus A. That means absolute value of fx minus f of A. over x minus a minus lambda less than epsilon. And if we write x equal to, consider this is the point x and this is the point a. If we write x equal to a plus a, where x belongs to a, j, and a is equal to x, then that implies a is equal to x minus a. Then x means a plus a. Now put the value f of a plus a is minus f of a over a is minus lambda less than epsilon. That implies, since x equal to a plus a, if we put the value, then this implies f of x minus f of a minus lambda, a means x minus a, less than epsilon times, here a means x minus a, epsilon times x minus a. That implies fx is approximately equivalent to f of a plus lambda x minus a. This is the approximately equivalent to. Some actually, as per example, since 1 over 1/3 is equivalent to 0.33, therefore fx is approximately equivalent to f of a plus lambda times x minus a. That means if f is defined from real line to real line, then f is differentiable at the point a. If f is approximately linear, that means fx equal to f of a plus lambda times x minus a plus small error, where this error divided by x minus a tends to 0 as x tends to a. That means f is differentiable at the point a means there exists a function f1 which is defined from j to r such that f of x equal to, notice here I have considered this lambda as f1. f of x equal to f of a plus f1x times x minus a. If we can to find this type of f1 where f of x equal to f of a plus f1x times x1, where this f1 is continuous at the point a for all x belongs to this interval j. If such f1 exists, then f prime a equal to f1a. Means when f is differentiable at the point a means I have to find there exists f1 such that when x not equal to a, then f1x equal to f of x minus f of a divided by x minus a, and when x equal to a, then f prime a equal to f of a. I hope my all viewers have understood. Now let's see one example. If we consider fx equal to 1 over x, then f of x minus f of a means 1 over x minus 1 over a, and this value is a minus x over ax, and this is equal to minus 1 over ax times x minus a. Therefore, notice here f1x equal to minus 1 over ax. Therefore, if f is differentiable at the point a, that means since we have to find such f1, if we consider fx equal to 1 over x, then notice all condition has satisfied. Here f1 would be such type. Okay, I hope my all viewers have understood actual idea. Next, I will see fx equal to mod x. Is the function is differentiable at the point 0? We all of us know this function be not differentiable at the point 0. But always I have checked check this function be differentiable or not as a wrongly. Always I have checked by derivative. But actually, this is the wrong way. For differentiability, we have to check fx equal to f of 0 plus f of 1 x times x minus 0, and this is true for all x belongs to R. That means actually we have to check, we have to find this type of f1. Notice if x not equal to 0, here fx equal to mod x, here f of 0 means obviously this is 0 and f1x x. When x not equal to 0, then f1x would be 1 for all x greater than 0 and f1x would be minus 1 for all x less than 0. And notice this type of f1, this type of function be not continuous at the point x equal to 0. Here I have got f1, but these f1 be not continuous at the point x equal to 0. So, fx equal to mod x be not differentiable at the point x equal to 0. And this is the actual main way to find a function be differentiable or not. But always most of person evaluate a function be differentiable or not wrongly. A function be differentiable or not, most of the person evaluate by derivative. But this is the actual way. We have to find such f1 in this way. And these f1 be continuous and the value of f1 at the point a is actually the derivative of this function, our given function at the point a. This is actually main way to find a function be differentiable or not. Now, f which is defined from real line to real line, f of x equal to x mod x, is f is differentiable at the point x equal to 0? For this, similar to before, this is very interesting. We have to check f is differentiable at the point 0. For this, f of x equal to f of 0 plus f1x x minus 0, and this is true for all x belongs to R. Here f of x means x mod x, f of 0 means 0, f1x times x. That means that imply f1x equal to mod x. Now we have to check, is this f1 be continuous at x equal to 0? Obviously, this f1 be always continuous at the point x equal to 0. So, f prime 0 equal to f1 at the point 0, this value would be 0. So, this function be differentiable at the point x equal to 0. I hope my all viewers have understood the method is easily. Okay? Well. Now, f defined from real line to real line. f of x equal to x square when x less than 0 and x cube when x greater than equal to 0. Is f is differentiable at x equal to 0? For this, the theorem is f of x equal to f of 0 plus f1 x minus 0 means x. f1 x times x actually. That means we have to find such f1 which is continuous function. Just put the value. Then since here fx equal to x square when x less than 0, then f1x would be such type x when x less than 0 and x square when x greater than equal to 0. And obviously the picture would be such type when x less than 0, then this would be x square, and this function is, this f1x is continuous at x equal to 0. So we can tell this function f is differentiable at x equal to 0, and derivative of the function, that means f prime 0 equal to f1 at the point 0. This value obviously equal to 0. I hope my all viewers have understood how we have to find differentiability of any function. Okay? Well, now I will say the differentiation function. What is the differentiability from real number to complex number? Similar to before, just as a review, here real number to complex number. So function defined from closed interval ab to complex number be given. Then we say that f is differentiable function at the point t where t belongs to closed ab if there exists a complex number alpha such that for a given epsilon greater than 0 there is a delta greater than 0 such that 0 not equal to h belongs to R mod h less than delta, imply t plus h belongs to closed interval AB. Then that imply absolute value of f of t plus h minus f of t divided by h minus alpha less than epsilon. These alpha similar to real differentiability in real, this is actually the derivative, means this is actually the new function similar to real, where in real this is, I have considered it f1, and here just consider this derivative, this the value of the limiting value of the derivative is alpha. So here just consider it as a notation alpha. And if f is differentiable at the point t if limit h tends to 0, f of t plus h minus f of t over divided by h exists, and this limiting value is alpha, where alpha is unique, then this alpha is called actually the derivative of this function at the point t, and this is denoted as f prime t. We all of us know this is the function of differentiability from real number to complex number, and differentiability only on complex number is u be an open set. A function f from u to c is said to be differentiable at the point j belongs to u if there exists alpha in c such that given epsilon greater than 0 there exists delta greater than 0 such that f of z plus h minus f of z over h minus alpha, this absolute value less than epsilon, and this is true for 0 less than mod h less than delta, and this number alpha is called derivative of the function f at z, and it is denoted by f prime z. That means f is differentiable at the point z belongs to u if the limit means limit h tends to 0, f of z plus h minus f of z divided by h exists. And if f is differentiable at each the point z belongs to u, then we can tell f is said to be analytic on the open set u. Another notation of analytic is holomorphic. That means is u denote the set of function, means set of holomorphic function on the set U. That means similar to real number. This notation is similar to let f be a function which is defined from U to C be given and z be the point in U, then f is differentiable at the point z if there exists a function f1 which is defined from U to C. This f1 is continuous at the point z such that f of w equal to f of z plus w minus z f1 w. Obviously this f1 is the derivative of this function f prime z equal to actually the f1z. The proof is such type. Let f be differentiable at the point z. Then define. At first I will prove the function f1 is continuous at the point z such that f of w equal to f of z plus w minus z f1 w. Define f1 w equal to f of w minus f of z divided by w minus z. This is true for w not equal to z and f1 z equal to f prime z. To check the continuity of f1 at the point z, let epsilon greater than 0 be given. And since f is differentiable at z, then for all epsilon greater than 0, there exists delta greater than 0 such that 0 greater than absolute value of w minus z less than delta imply fw minus f of z divided by w minus z minus f prime z less than epsilon, since f is differentiable. By the definition of differentiability, we can write this part fw minus f of z divided by w minus z means f1 w. That means this implies absolute value of f1 w minus f1 w and f prime z means obviously f prime z means f1 z. Therefore absolute value of f1 w minus f1 z less than epsilon. This is true for absolute value of w minus z less than the delta. Therefore by this expression we can tell f1 is continuous at the point z. Therefore our proof has done. If f is differentiable, then there exists a such type of function and this function f1 is continuous and this f1 is actually the derivative of this function. Similar to real line, just as a review in complex part, because our actual concept about the complex part. So just recall, just consider, I have considered again this part. Conversely, if f1 exists where f1 w equal to f of w minus f of z over w minus z, and this is true for all w not equal to 0. Then we have to prove f is differentiable at z and f prime z equal to f1 z. Then by the continuity of f1 at z given epsilon greater than 0, there exists delta greater than 0 such that 0 greater than absolute value of w minus z less than delta, that imply f of w minus f of z divided by w minus z minus f1 z less than epsilon. By the continuity we can tell this is, and notice from this is we can tell f is differentiable at the point z and f prime z equal to f of z. I hope my all viewers have understood all part. Okay? Well, consider as for example fz equal to z square. Then fz minus fz0 would be z square minus z0 whole square. This is equal to z minus z0 times z plus z0. Then notice by this equation here f of z equal to f of z0 times z plus z0 times z minus z0. Therefore, by this equation we can write f1z equal to z plus z0, and obviously this function is continuous at the point z0, and f1 z0 is z0 plus z0, which is 2z0. This is the derivative. That means f prime z0 equal to actually f1 z0 and this value is equal to 2z0. I hope my all viewers have understood this equation, this question, this example. Okay? Well, I will leave out one example for all my viewers. The example is f be a function which is defined complex number to complex number be given by fz equal to z to the power n, and this is true for all n belongs to natural number. Then show that f is differentiable and f prime z equal to n z to the power n minus 1. This is the same type of example, fz equal to z square. Just try it. Okay? Today I will stop here. In my next video I will discuss this type of question again briefly. Okay? See you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.